Can you see my screen?
Yes, we can see your screen.
Wonderful. Okay. Thank you. Yes. So this is my title, and it's a great honor to be here. I've got quite a lot of slides, so I'm going to go through them quite fast, but I think they will be accessible afterwards. I want to just start off reminding you about the formation and evaporation of primordial black holes. As you've heard many times, black holes of arbitrarily small mass can form in the early universe, and they naturally have a mass which is of order the horizon size when they form, which would go down to 10 to the minus 5 grams if they formed at the Planck time. But at the QCD epoch, it would be 1 solar mass, but they might in principle form as late as 1 second, so it could be as high as 10 to the 5th solar masses. And as we all know, they radiate with a temperature which goes like 1 over the mass, and they evaporate therefore on a certain time scale. And black holes of 10 to the 15 grams, they're the ones which are exploding today, where in principle we might see the final explosive phase. I refer to black holes which are smaller than 10 to the 26 grams, the mass of the Earth, as quantum black holes, because their temperature is more than the temperature of the microwave background. Now, this is my favorite. The formation mechanisms I'm really not going to go through because you've heard so much about this, but just very briefly, they can form inhomogeneities. They can form if there's a softening in the equation of state. They can form from cosmic strings. I don't think there have been talks on that, but in principle, strings can self-intersect and collapse with some small probability. They can form from bubble collisions if there's a phase transition in the early universe, and they can even form from the collapse of domain walls, and they can then be rather large. This is my favorite diagram. This shows all the scales of structure in the universe from the Planck scale. As you go at the top, go in an anti-clockwise direction, the scale goes up by a factor of 10 for every minute, and it goes all the way up to the scale of the observable universe, so all the structures in the universe are shown here. But what's important for this talk is that I'm putting around this diagram all the black holes according to the different masses. So there's the solar mass black holes, which we know exist, well, the stellar remnants, I should say, intermediate mass black holes, the black hole in the center of the galaxy, the black holes powering quasars. Some sense the universe as a black hole, and then on the left we've got smaller black holes with the terrestrial mass, lunar mass, the ones that are evaporating all the way up to the Planck scale. And I love this diagram because it just shows how pervasive black holes are. Most people focus on particular types of black holes, but if you're obsessed with black holes like me, you see them everywhere. And I also like this because down the division in the bottom is between quantum and classical black holes, and it's up at the top that you get the possibility of higher dimensions. I just want to say a little bit about the universal black holes. I don't normally talk about this, but there are the black holes forming, of course, in the middle, if you like, at the top. And I just think it's interesting. In some sense, the whole universe could be a primordial black hole. And this is very speculative, but I mean, there are different approaches. For example, Smolin has the idea that when a black hole collapses, it can generate a baby universe. So in principle, our whole universe could have come from a primordial black hole. I think slightly more plausibly, or more studied, is that in brain cosmology, you can in principle, our universe is described by the 5D Schwarzschild Sitter model, in which case, in some sense, it emerges from a 5-dimensional black hole. And you'll remember that you've got high-dimensional black holes up at the top there. And, you know, especially being inspired by Alexander Dolgoth's lecture, you really have to ask, well, are almost all black holes primordial? And if you look at this Ouroboros of all the black holes, the only ones we really know are non-primordial are this little range here where they can form from stellar collapse. So I'm becoming a little bit obviously obsessed with the topic, but you know, it could be that really the astrophysical black holes, which most people take for granted, could just be a very small fraction of all the black holes that actually exist. Now, the formation of black holes, this has been talked about. I'm sure you're all aware that if you've got a spectrum of fluctuations, in order for an overdense region to collapse, it's got to be bigger than the gene's mass. So if there's a pressure parameter alpha, you have to exceed some critical value, and you have to compare, which in this simplistic analysis, which I gave in 75, just says that the horizon amplitude fluctuation must be bigger than alpha. And you just have to compare that to the expected fluctuations on the horizon scale, and you get this well-known exponential formula. In other words, only a tiny fraction is going to collapse. This is the first paper I ever wrote, by the way, and it's my most cited paper, which is rather depressing in a way, because it means that my career has been downhill from the start. But still, it was really just a very simplistic approach, but more sophisticated calculations, which I haven't got time to go into, have obviously made it much more rigorous. But the other thing you can ask is, what fraction of the universe went into primordial black holes? You just compare the present density of the black hole to the microwave background density. That could be quite large, that ratio, but as you go back in time, the fraction, the matter density, the PBH density, goes like 1 over r cubed, the radiation density like 1 over r to the 4th. So you can show the fraction related to the time. So we both require and expect beta m, the collapse fraction, to be tiny. And that's going to come back towards the end of the talk, because you've got to explain that fine-tuning problem. Now, I want to just elaborate a bit more on these constraints, because if we ask what is the constraints, obviously the ones which haven't evaporated, they've got to have less than the CDM density. If they've evaporated, they have to have less than the gamma ray background density. If they evaporated in the past, they have all sorts of effects on the background radiation, and they generate entropy and Big Bang nucleosynthesis. So this is some constraints. The shaded region is excluded. This is beta as a function of mass. And of course, because of that formula I gave you relating beta to epsilon, that gives you an expression for a constraint on epsilon, the horizon scale fluctuations, as a function of mass. Now, so you can see you need big fluctuations of order well over 1% to make black holes, and on the observable size, for example, the Planck scale, I put Kohri here, rather out of date, it's only about 10 to the minus 5. So what you know, the first point is that this is a unique probe of the density on small scales, but also you need either a blue spectrum or you need some special feature to make primordial black holes. Now, for a lot of my career, I've been working with colleagues on constraints on primordial black holes, because we don't, except perhaps until recently, have any evidence for them, but the best you can do is get constraints. And this shows a huge range of constraints which come from lensing, evaporation, annihilation, gravitational waves, disruption, microwave background, etc. And so I want to just go into a little bit of detail, but I won't go into much detail. I just want to overview some of that work, because that's what so much effort has been put into. This is a paper, the review I did with my Japanese colleagues in 2010, looking at constraints on evaporating black holes. And I don't want to go into detail, but all the coloured regions are basically excluded. We've had some talks on this. This is from Big Bang nucleosynthesis, the gamma ray background, extragalactic cosmic rays, neutrino relics, CMB distortions and things like that. But this is an old paper. This is 10 years old, and it assumes a monochromatic mass function. There have been many more recent papers. I'm just flashing some up here. Obviously, you've heard about some of these. This is the Stefan Profumo talked about this. This is the constraints which we just heard from Dr. Laha on the galactic center observations. Sorry, I think I've got this the wrong way around. But sorry, this is the Boudard and Corelli limit from the electron-positron constraint. This is the Coogan et al. Limit, and this is the limit we just heard about from Dr. Laha. Also, it's interesting to look at the constraints which come from the CMB anisotropies and the spectral distortions. And I'll just flash up some pictures. We had a nice talk from Dr. Khatri about that, and I'm just showing their constraints. So as a result of all this, the constraints are now much more much more complicated than they were before. This is the review which I'm doing with my Japanese colleagues. It will appear soon. It's on the archives, and this just shows all the constraints for the evaporating black holes put together. And obviously, it's quite complicated, and it's actually rather hard to keep up with the literature. But now, what about the non-evaporating black holes, which in principle might be the dark matter? This is the paper I wrote with Kuhnel and Stansted in 2016, and now I was quite amused because when Stefano gave his talk, he put in big letters, "This is wrong," and it's right in a way. I would say it's wrong partly because some of it's right, but in particular, the point is a lot of these limits are now thought to be wrong. We've heard about this, the femtolensing, the neutron star limit, and even the accretion limits have been updated. But I want you to refer to the more recent paper with Florian, which is this paper, which has just appeared. And I want to stress that these constraints are right. And you can see they're quite a bit different because some of the ones which are wrong have been removed. But I have to be careful. It's only right for now, because undoubtedly within, as time goes on, some of the constraints will change or go away. And also, I quite like the idea you can represent this figure in terms of red by breaking it down into different redshifts, which is nice. I think it was my colleague Juan Garcia Bellido who first did that, so that's quite a nice representation. But the point about this diagram on the left is that you can see that there's certain mass windows where you can have a lot of mass, conceivably even the dark matter. There's the intermediate mass range here, there's the sublunar range here, there's the asteroid mass range there. You could even have stupendously massive black holes. I'll come on to those later. And in principle, you could have Planck mass relics if evaporating black holes left stable relics. Now, by the way, I really enjoyed Stefano's talk where he gave another classification of the different names you could have for some of these. This is sort of like a breaking down of subgroups. So I found that rather amusing. So I'm just flashing that up again to remind you. Now, of course, those constraints, at least the original Japanese constraints, have been modified in all sorts of ways. We've heard, I think you will have heard the talks about the constraints from the Subaru observations. There's the detection by analyzing the Ogle data, and there is an interesting limit which comes from the microlensing of supernova, which from Zumul, Karogue, and Zoljak. This is controversial though, because I know Juan disagrees, and well, I sort of disagree, but on the other hand, it's controversial, and I think it's an important thing one has to decide whether this is true, because if so, it's going to rule out some of these dark matter models. There are constraints from LIGO. I'm just flashing these papers up, but I'm not going to let you have time to look at them. This is the final constraints diagram, which comes from the paper with the Japanese colleagues. And it's tremendously complicated because this just represents a huge number of constraints you've got. And again, coloured regions, this is FM, the fraction of dark matter as a function of M. All the coloured regions are excluded, and they're all, these acronyms tell you what sort of constraint it is. Obviously, I can't go through these now. It's a little bit easier if I break it up into the lensing, dynamical accretion, and cosmological background constraints. I can really only recommend that you consult the paper. Obviously, everybody's producing diagrams like this all the time, so I'm not going to cite all the people who made similar papers. In fact, almost every paper now has a diagram like this, but we're trying to put them all together, which is very difficult because people produce papers on this faster than we can read them. But anyway. And one thing you can do, I showed you in the first part of the talk how you can go from the constraint on beta to a constraint on the power spectrum. Well, you can do the same thing with all these new data, and this is the sort of constraints you get on the power spectrum. Several other groups have written similar papers, but I'm just obviously focusing on my own. Now, but I do want to stress, because, I spent most of my life working on primordial black holes, and it somehow looks as though I'm just putting nails in the coffin by showing all these constraints. Because when you look at something like this, the message might seem to be, well, they can't be. I mean, there are some gaps, but they can't really exist at all, which isn't good news. So I just want to stress all the constraints have caveats and may change. So that's why any figure like that which I've just shown will be wrong, at least in part, eventually. Each constraint is a potential signature, as we will see, so it's not just purely negative. And PBHs, I want to stress, are interesting even if F is much less than 1. We shouldn't be too obsessed with whether primordial black holes provide the dark matter. I mean, arguably the most important component of the universe is human beings, but we only comprise a tiny fraction of the density, and it's a bit like that with primordial black holes. Now, obviously, the issue which is all interested this workshop is, can primordial black holes provide the dark matter? You've already heard the reasons, but the main argument against it is the fact that you do require fine-tuning of the collapse fraction, which I'll come back to in a moment. And obviously, it's the claims from the LIGO-Virgo work. Sorry, Kagura is the forthcoming Japanese one, which have provided much of the reason for the interest in this subject, because these are the black holes they've discovered, and they're more massive than you would expect, and so this raises the question whether there are non-standard population. Could they be population 3, or could they be primordial black holes? Obviously, people at this talk, in this meeting, probably quite like the idea they're primordial, but one has to be honest and say that that's not the mainstream view, but hopefully it will become the mainstream view. And there have been many talks on this topic, so I won't go into that anymore. I want to spend the last part of my talk really talking about the cosmic conundra which primordial black holes can solve. And these are a list of all the papers. These are with my colleagues, Sebastian Kless and Juan Garcia Bellido, and Florian Kuhnel and Luca Vicinelli. So there's quite a lot of papers here, and I'm just going to flash up brief summaries of these papers. Now, you heard a nice talk from Chris Burns about the PBHs and of course also from Dutta, PBHs forming at the QCD phase transition because there's a softening of the equational state. And I do want to stress that it's Carsten who really first drew attention to this in his 1996 paper. But what in the paper with my colleagues, the Cosmic Conundra paper, we sort of extended this idea by pointing out that you've actually got lots of little bumps in the equational state. And this means that you will have lots of little bumps in the mass function of the primordial black holes. This is assuming the famous beta, the expression for beta. It depends on what the fluctuations are and what the power spectrum, what the index is of the power of the fluctuations. These aren't the fluctuations which are observed on the CMB scale. We need another spectrum of fluctuations on the smaller scale to make the PBHs. But you have a nice prediction of what the mass function should be, and basically we argue that you need a spectral index of about 0.97, and this gives you a peak at 2 solar masses, another peak at 30 solar masses. So the peak, that will be the dark matter, the 30 solar masses is going to be the LIGO events, and then we've got other peaks at 10 to the minus 6 and 10 to the 6 solar masses. So what exactly are these? These are the constraints, which is why we argue that you need roughly 0.97. I have to be honest and to say that we recently revised the calculations and it's now becoming 0.96, but I'm only going to present the result as it was more recently. Now, a crucial question is going to be whether the primordial black holes are clustered, because there are lots of constraints here, and in theory the microlensing constraints do not allow you to have the dark matter in this region. But the counter argument is all to do with whether the black holes are clustered. This is a really important topic. I'm citing the papers by Juan and Sebastian Kless, arguing that they're clustered, and this gets around the various microlensing. But one has to confess this is controversial, and not everybody, even in this audience, may agree with that. But this is the crucial question. If you want them to be the dark matter, they better be clumped. Now, what are these conundra? The first conundra is the Nikora et al. Detection way down here at this low mass. So we're claiming that that's the bump there. I'm going to go through this fast. You obviously, I'll go through it so fast you probably won't have time to criticize it, but the other possibility is that there's evidence for microlensing of quasars. This is associated with this bump too. This is an argument Mike Hawkins has been pushing for years, but is now becoming more mainstream. There is the excess of lenses discovered by Ogle and Gaia in the mass range where you shouldn't get them from black holes. So this is bump 3. This is some of the data there. There's the claims that there is a correlation between the cosmic and X-ray backgrounds, which can be associated, which is evidence that there were primordial black holes that formed early. If you've got the primordial black holes, they form early structure because of the Poisson fluctuations, which generate X-rays from the black holes and the infrared radiation from the stars. And so this is the bump there. This is the
You have 5 more minutes.
Oh no, never mind. I'm nearly there. Then the ultra-faint dwarfs, the idea is that if you've got black holes in halos, they'll disrupt the clusters. The dwarf, these are the ultra-faint dwarf galaxies, they'll be disrupted. So there should be a noticeable absence of them. And there is, in fact, apparently evidence for this. And this is bump 5. This is some simulations by Baldrini et al. Now, of course, the really exciting one is the LIGO Virgo. Now, obviously, we're claiming that the 6 bump is associated with LIGO Virgo. Now, and this is, I'll remind you what the spectrum is. We were really excited because we predicted before the LIGO 3 run where we would find events, and they seem to be there. And lo and behold, that's where they were. So we found that we were really excited by that because we predicted where they were, and they were. Now, of course, now there are far more events than 3, but and it's a more complicated analysis. So obviously I'm trying hard to sell this picture to you, but you can obviously disagree if you want in the question session. And then the final one is to do with the possibility that the supermassive black holes are seeds for galaxies and quasars, and this was a view which Sasha Dolgov talked about, and this is our prediction. This is bump 7, so we're claiming bump 7, which is the one associated with the electron-positron annihilation. The point is that if you have NS is 0.97, you naturally predict the observed ratio between the black hole and the galaxy mass. So that's nice too. Now, there's the fine-tuning problem. I'm going to go over this very fast because the point is that I've told you about the mass and the collapse fraction, but the fine-tuning is this. First of all, why is beta so small? But the other question is, why is the ratio of the PBH density to the baryon density almost 1? I mean, it's actually 6. And that's a really strange thing. Why should the baryons and the PBHs have such a comparable density? Now, in this paper, we have a sort of anthropic argument, which is basically says if this ratio was too big, there wouldn't be enough baryons left over to make galaxies. If it was too small, the fluctuations would be too small to make galaxies. So there's a sort of anthropic reasoning that chi has got to be pretty of order 1. I mean, it's 6. But the other interesting thing is, of course, the black holes forming at the QCD epoch, as Christian Burns emphasized, they have the solar mass, but also the collapse fraction beta is necessarily of order eta, which is the cosmic baryon to photon ratio, which is about 10 to the minus 9. And so that was really a puzzle. I mean, how do you explain that tuning? And the most obvious answer is to say, well, maybe the PBHs actually generate the baryon asymmetry. And this was the focus of the paper with Garcia, another paper with Juan and Sebastian, where we argue that when the black hole collapses, that actually it generates an outgoing shock wave, rather like a supernova, and the shock wave gets so hot that it can, in principle, produce a baryogenesis. And we have a very precise calculation. We argue that the CKM matrix generates this, and we argue that to produce the baryon-photon ratio we need to have a value of gamma. Gamma is the size of the black hole relative to the horizon of 0.8. Well, the results from people like Musco et al. Do give a value like that. So we were rather excited. So the idea is that around each black hole you get a photon to baryon ratio of about 1. A baryon to photon ratio is about 1, but then when it diffused to the rest of the universe, it automatically gets reduced to beta. So we were excited by this. Now, I know there is skepticism among some people about this result, because it's to do with the fact whether you get this CP violation and whether they can diffuse, and I'd be quite happy to be criticized about this. But nevertheless, I'm still excited about it, because there is the fact that eta twiddles beta. I mean, it has to be telling you something. You still need the fluctuations, of course, and this is the other part of the paper where we talk about a model of inflation, where you have a second inflationary phase, which is this is the basis of the anthropic fine-tuning. Now, the other thing we didn't count it as a conundra, because it's too recent and maybe too questionable, but we've heard a lot about the nanograv signal, and there have been 4 papers on this, which I'm flashing up briefly here, and there are more papers coming out. In fact, there's probably another paper coming out even as I speak, claiming that the nanograv can be explained by primordial black holes. But I mean, I'm confused, because actually Yassine on the first day said that it wasn't a signal at all, but maybe we can talk about that. Now, I want to end by talking about the work I've done with Florian Kuhnel and Luca Vicinelli. You notice that in the constraints there's a huge gap between 10 to the 14 and 10 to the 19 solar masses, where there are no constraints. So we are interested in that, because I mean, obviously no one believes these are what we call stupendously large black holes, or slabs. I mean, nobody's going to believe the dark matter's there. They wouldn't fit into galaxy halos. But on the other hand, we know they're supermassive black holes in the centers of galaxies that go up to 10 to the 11th. And what we found that the best constraint, maybe the only constraint, comes from the well-known argument that if you've got the dark matter in WIMPs, they'll accumulate in halos around the black holes and annihilate and produce a gamma ray signal. And so this is in our paper, this is the constraint we get from this analysis. The blue region, this is F against masses excluded. And incidentally, you might say, well, if there are these slabs, where would they come from? And I like the talk by Dr. Takistov, because his model, where you form black holes from bubble multiverses, actually, he only showed it down to the SMBHs, but if you extrapolate that to the slab mass, you get slabs. So it seems to me a feature of that particular model that they will have slabs. So but the second paper was to do with more conventional black holes. This is our paper, Black Holes and WIMPs, All or Nothing or Something Else. And this is a well-known problem. WIMPs and PBHs are not compatible. I think Kristen Burns talked about this. I explained the reason. The WIMPs, if most of the dark matter is in WIMPs, they will clump around the black holes and produce gamma rays, which basically excludes having many black holes. So this is the excluded region. But the point is, these previous analyses were only done for a relatively modest range of masses. We've extended the PBH mass range from 10 to the minus 18 to 10 to the 15, and we've allowed a WIMP mass of 10 GeV to 1 TeV, and we've got both a galactic and extragalactic background. And here are basically our results. So this is FB against M. This is the previous diagram, but extrapolate it to smaller masses. And so this first diagram assumes that most of the dark matter is WIMPs, and these are the constraints you get on PBHs. The second diagram is if the dark matter is in PBHs, and then you get a constraint on the WIMPs. So the point is, for most of the parameter space, one component completely dominates. So the dark matter is either PBHs or it's WIMPs. Can't be both. In particular, the fraction above 10 to the minus 9 solar masses, the fraction in PBHs has got to be, if it's above 1%, this will exclude the WIMP scenario. So, for example, if you believe that the LIGO black holes are PBHs, you exclude the WIMP scenario. But there is one little range, you notice, that's what I said there. There's one little range. If the PBH is sufficiently small, down here, you could still have a large density in PBHs and WIMPs. And of course, some people are arguing for small PBHs. So there's still a little window where you could have it. But actually, the point is that for most scenarios, if LIGO has less than all the critical density, maybe 1%, the WIMPs have to have less than 1%. And that means you have to have a third dark matter component. And that was the significance of the title, All or Nothing or Something Else. So let me now finish. PBH studies have led to profound insights, blah, 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 into fundamental physics. most work recently has been focusing on constraints, but now at last we have possibly positive evidence coming from cosmic rays, dark matter, LIGO, Virgo, and the other conundra I talked about. Obviously, these are distinct roles, and primordial black holes are important if they explain any of them, but if you have an extended mass function, you could, in principle, explain all of these things. And I mean, that was the sort of message we got from Sasha Dolgoff's talk, that PBHs can explain everything. And obviously, I'm pushing that view now. If you have an extended mass function, such as you might naturally get if you've got the bumps I described due to the phase transitions. And then I like the idea, how do you get over the fine-tuning problem, which is the main criticism? Well, it naturally is explained if at the PBH form at the QCD epoch, and then there's some baryogenesis scenario, such as I referred to, which is going to produce the barrier symmetry. So thank you very much. I might have, no, I don't think I have overshot. Thank you very much. Over to you.
Yeah. Thanks a lot. So the first question is from one of our YouTube viewers, Akka Bhattacharji. What is the difference between normal black hole and quantum black hole?
Well, I mean, they're different definitions. I defined a quantum black hole as being a black hole whose temperature is higher than the CMB temperature. And that corresponds to the mass of the Earth, 10 to the 26 grams. And it's at the bottom of that Ouroboros diagram I showed you. That's rather, it's a nice symmetry. It's right at the bottom there. That's because if it was cooler than the CMB, the black hole wouldn't actually evaporate because it would be accreting the CMB. So in practice, a black hole is only a primordial black hole because only primordial black holes are evaporating. But in principle, in practice, a primordial black hole will only evaporate if it's cooler than the CMB. I mean, at the present epoch. I mean, obviously you should be doing it at the epoch. But there are different definitions. Some people talk about quantum black holes, the ones that form in accelerators if you've got, you know, large extra dimensions. So not everybody uses the word in the same sense. But I use it to mean that quantum effects, i.e. Hawking radiation, is important.
So next question is Swagat. So you can unmute your mic and ask the question.
Hi, Professor Bernard. I wanted to ask, we usually ask this question that is it possible for a bigger primordial black hole to form on top of a smaller primordial black hole? And it's usually answered that it's a very rare process. How rare is it, and can we quantify this?
Well, you see, if the fraction of regions collapsing to black holes is small, and for example, I said it's 1 in a billion if they form at the QCD phase transition, but much less than that if they form earlier, it's a very low probability process. However, you've got to realize that you're forming the black holes from the Gaussian tail. And if you're in a Gaussian tail, I mean, you're going to be in a region which is more likely to be collapsing as well. So there is an enhanced probability that a small black hole could be contained in a bigger black hole, even though the probability is small. But I think another important point is that if you've got black holes, the black holes themselves can act as a source of structure. Because if you've got a black hole, it produces either through the seed effect, its Coulomb effect, or through the Poisson effect, it does generate larger scale structure. And that larger scale structure might be like the first, you know, dwarf galaxies or something, but it could in principle give rise to black holes as well, because you've got the Poisson fluctuation. So there is a sense in which if you've got a small black hole, there's a higher probability it might end up at the center of a big black hole. But the other point is the small black holes, if you have a population of them, may generate fluctuations which could also generate big black holes. But generally, I mean, it's people have thought about this, but in general, it's a low probability thing.
Thank you.
The next question is by Christian Barnes. Please unmute your mic and ask the question.
Oh, hi, Bernard.
Hi, Chris.
Well, I had a couple of questions, but if I just stick to one for the moment, and you kind of answered it in your talk, but you said, so the stupendously large cannot be all the dark matter because of galaxy rotation curves. But
well, I mean, you can't. What I mean is, you can't fit one into a halo. They're bigger than a galaxy.
Indeed. So can't you give a constraint? Because in your constraint plot, you allowed FPBH of 1. I'm wondering sort of what fraction of the dark matter.
Well, no. I mean, the point was, I don't allow. Let me just go back to this constraints diagram. I mean, the point is that the reason there are no constraints is basically because nobody's thought about it. because most people would think, well, it's crazy. Who's going to believe in black holes that big? There are constraints here which I haven't shown. For example, there are constraints that come from accretion, but there aren't dynamical constraints, I should say, because this is the constraint here. I think you can see my little mouse arrow. That's the constraint that comes from the disruption of tidal distortions of galaxies. The CMB is the dipole constraint, because if you have some of these big black holes in the universe, they will attract us. They will give us a dipole, you know, a dipole motion. And so there is a constraint that comes up here. The incredulity limit, this limit here, incidentally, corresponds to one black hole per universe, which is in a sense trivial, but people don't often think about it. But there is this big region here. Now, there are constraints. One constraint would come from anisotropies in the CMB on large scales, but also constraints come from accretion. And actually, I mean, even I've done accretion calculations which show, and in fact, this paper discusses the accretion constraints, and there are constraints, they come down, but they're actually much weaker than these constraints. So the accretion constraints are aligned something like this, but accretion is really complicated when you're dealing with a stupendously large black hole. And to be honest, I don't even though we give a calculation, I don't really believe it very much. I mean, all the we had a beautiful discussion of accretion by Yassine, for example, earlier in the workshop, but that only works up to black holes of about 10 to the 5th solar masses. So it just happens that the best limit does come from this limit, which of course you were one of the people who wrote about, Christian. You know, but this is just extrapolating it to the very high mass range, and so
this assumes the rest of the dark matter is a WIMP. Which we don't know.
This diagram here assumes that most of the dark matter is a WIMP. And of course, if you don't believe that, this is the more general. This diagram here on the left is the more general one. So, and let me just, because I want to stress to the audience that that Christian was one of the people who wrote one of the important papers showing that WIMPs and PBHs are not compatible. And the only thing I would say, Christian, is that they're not compatible unless you go to they are compatible if you go to small enough PBH mass.
Yeah, I totally agree with that. And we said in our paper that it's more than a millionth of the mass of the sun is what we could sort of talk about.
Yeah, we made it a billionth, but it's where this line hits the the gamma ray background limit. Yeah.
Okay, thank you.
Thank you.
We have time for a few more questions. Suchetna Chatterjee. Yeah.
Hello, I just had like 2 quick questions. The first one is in the Carr et al. 2020 plot where you updated the constraints. Did it have the monochromatic mass functions? Because the mass functions matter, right? I mean.
Oh, absolutely. I'm not going to show the figure. It takes me too long. Yes, that figure is for the monochromatic mass function. I mean, most people, when they plot the figure, do it for the monochromatic mass function. When you have an extended mass function, which is almost certainly the case, I mean, no one really believes you form PBHs with a monochromatic mass function. And what's more, we can predict, there are only a few predictions as to what the mass function would be. I mean, for example, in many inflation scenarios, you get the log normal mass function. This is something which Sasha Dolgov talked about, and indeed he and Silk wrote, I think, maybe the first paper on that. Critical collapse gives you another mass function. And if you have a mass function, all the constraints have to be reconsidered. And the point is, in fact, this was discussed in the talk by one of the talks yesterday, that the constraints change because you have to be very careful. You can't just take the monochromatic mass function. I'll see if I can get back to it. I probably can't. You can't just take the FM constraint diagram and plot the extended mass function, because it doesn't work like that, because what happens is the limits themselves. So if we take these colored lines, okay, this is for monochromatic mass function. If you have an extended mass function, then you have to, the limits themselves change. You see, it's you might think it's easy to get around the constraints by having a monochromatic mass function, but it's not, because it's true that by spreading out the mass over many decades, you might think you can lower, the density in any particular mass range. But the problem is that if you've got an extended mass function, you may be able to have the dark matter at one range, but then the tail, where it's got lower density, is still going to clash with one of the other constraints. So it's a very tricky question, knowing whether having an extended mass function makes it easier or more difficult to have the dark matter, for example. If you have a bumpy mass function, such as I talked about in the paper I did with Juan and Sebastian and Florian, then again it's even more complicated, because in that case you've got lots of bumps, and it's not so easy. All you can do is to actually do the calculation and see whether you are consistent with the constraints. And of course we claimed in our paper that we do just about can satisfy the constraints. Here's our bump, and this is an extended mass function, that's what I mean. And here are the constraints which are plotted. Now those who are sharp-eyed will notice that you may have problems up here at the large mass range, where you could have conceived, especially clashes with accretion constraints. But I'm not saying everything's hunky-dory, but nevertheless, it's a really important point that in practice we're always dealing with an extended mass function, and that's one of the reasons all the constraint diagrams, when they're monochromatic, have to be dealt with very carefully.
Thank you. So I think I would move for others. If we have time, I can ask the second one, but
well, just send me an email if not. Yeah.
Okay, thank you.
We have time for one more question only. And the rest of the questions, there are many more questions, but I request the speaker to look at his chat box and directly engage with.
I will look at the chat box, yeah.
Just last question is by Ajit Srivastava. So please unmute your mic and ask the question.
Hello.
Hello.
I may have missed it. You mentioned about this shock wave from the collapsing matter for a PBH near QCD scale.
Yes.
Now, outward shock wave results normally from a hard core, like for supernova. So in this case, how does the outward shock wave arise?
Well, because when you do this, I mean, you see, when we talk about you have an overdense region which stops expanding and collapse against the pressure, and most of the focus has been on the question of what happens to the collapsing matter. But the point is, let me just find the relevant slides. The point is that here we go. Sorry, let me just find the slide. The point is that you generate a lot of energy in this process, and that energy can be, this is the actual energy here, which is gamma is the size of the black hole relative to the horizon. This is the energy which is being generated just by the release of Coulomb
gravitational binding energy.
It's the gravitational energy,
okay,
and that energy gets imparted to the shock, and you get an effective temperature. Now, the CP violation factor in the CKM mechanism does depend on the temperature. Here's the formula, but the point is that it's a subtle question what T is, because this T is not T effective, because that would give a tiny effect. I think it's the geometric mean of the T effective and basically the QCD temperature. The real expert on this is Juan, and I don't know if Juan is in the audience, but however, I think if Carsten is in the audience, I know he's unhappy with the scenario because it makes the assumption that the protons and neutrons which are generated in the shell have got to propagate throughout the universe, and the argument against it is that no, they can't propagate freely because of all the cross sections. Our counter argument to that is that although the protons can't propagate freely, the neutrons can. But to be honest, it's a very difficult problem, and the calculation needs. Is Carsten there? He could comment.
Yes,
perhaps.
I'm here. Yeah. No, I do confirm from the simulations which we had done 20 years ago that the outer core, like around where the black hole formed, actually sends out a pressure wave, which like makes your energy density like be much larger than the average energy density. So it is conceivable that you can get to higher temperatures. I am worried about when you want to essentially produce a solar mass of baryons locally to homogenize them before Big Bang
Yes.
synthesis. That's my main worry in this scenario.
I appreciate that. And I mean,
Bernard and Carsten, I'm in the audience. I've been listening, but waiting for you to respond. So indeed, the motion of relativistic particles in plasmas is well studied. We understand how protons scatter off, and indeed, it's mostly through electromagnetic interactions. Now, neutrons do have electromagnetic moments, magnetic moments mostly. So they do interact also with the plasma. But if you work out the equations in an expanding plasma, you see that those neutrons reach much further distances. Actually, they actually get to the other black holes in sufficient time, 10 to the minus 2 seconds, to homogenize this barrier number. Now, of course, neutrons interact with neutrinos in a very dense plasma before 1 MeV, as you know, when neutrinos decouple, and they convert into protons again. So there is a transmission of the barrier number through neutrons out and a conversion back into protons through neutrinos. And this gives rise to a diffusion of the barrier number before nuclear synthesis.
This was my thesis topic, inhomogeneous Big Bang nuclear synthesis.
Right.
At the time, there were hopes.
We could discuss this afterwards.
Because right now, with the current observations, you have to have a universe which is essentially really homogeneous, well below delta rho baryon over rho baryon of unity. And anyway, it's something to be studied. Somebody should.
Anyway, indeed, and I have to say that I'm so glad Juan is here to defend me, because actually it was really his idea, this part of the paper, and both Juan and Carsten are much more expert on this topic than me. All I can say is that I'm really impressed with the fact that eta is beta, and I just want some way to explain why eta equals beta, because then the fine-tuning problem is solved, and one can, as both I think Carsten and Juan are saying, this is a difficult problem, but at least all I'm saying is I really think there's something significant about the fact that eta equals beta. I mean, it's even the same word almost.
Could I ask one question?
We need to stop I'm sorry, I will stop the session now.
Okay.
I mean, we can continue. You can continue the private chat.
I will carry on. I will stop sharing, but I will be able to have a chat now. I can read some of the
because there are many more questions, so you can probably please look at the chat and because
okay. Is the chat preserved? I don't know. Can I see this chat after it's preserved?
Yeah.
Okay.
So please look at the chat, and then you can because we need to start the next session in 10 minutes.
Of course. Oh my goodness. I'm sorry. It went on too long.
Thanks a lot.
Okay.
Let's thank all the speakers of this session and close this session. Thank you very much.